Playing pool poses a number of challenges for humans that translate into interesting problems in robotic manipulation, including precise cue control and strategy, many of which the literature has already made some progress on. Successful gameplay requires a combination of directional accuracy, velocity control, and strategic planning to maximize chances of winning. Our project aims to replicate and extend human capabilities in the game of pool. In a setting with multiple balls on the table, we use planning to select a ball and a pocket to aim for, and trajectory generation to execute the shot.
Our simulation setup involved creating SEF files for the cue, balls, and table. Our pool cue is welded to the last link of the EWA arm and uses a compliant hydroelastic collision model to replicate the effect of a leather Q-tip. Pool balls and table use rigid hydroelastic collision models. We created the pool table with CAD, accurate to bar size regulation tables. We attempted to generate the collision geometry using the script from class, but the convex decomposition algorithm resulted in inaccurate geometries. So we used primitives to redefine the collision geometry.
Now that we have the pieces of the simulation, we focused on the process of making a single shot. Given the ball poses in table geometry, we run task planning to generate a shot orientation and velocity. This is passed into trajectory generation to create a series of keyframes defining the pose of the cue throughout the shot. Inverse kinematics planning translates these cue poses into robot states, and the inverse dynamics controller uses the robot state keyframes to actuate the robot in the simulation.
Going more into depth on our first step of task planning, we are searching for the best ball-pocket combination that would maximize its chances of sinking the ball. We used the concept of allowed angular deviation from Neerhoff, which is the amount one can deviate from the optimal cue position and still be able to pocket the ball without cushion contact. A greater allowed angular deviation means more margin for error. We define the angle of our hit to be relative to the x-axis in the world frame. We calculate the allowed angular deviation for every pair of ball and pocket combinations if the shot is feasible. This calculation follows several steps to narrow the range of allowed angles to ensure a feasible shot while avoiding collisions. We then select the greatest allowed angular deviation as the shot to make and take the midpoint of this angle range that will sink the ball as the angle at which we want to hit the ball.
To generate the trajectory, we define 5 states for our cue: pre-strike, pause, strike, pause, and post-strike. In pre-strike, we position our cue at the calculated yaw angle at a set distance behind the cue ball. We pause for 1 second to allow the cue to stabilize at the desired pose. Next, we strike the ball and follow through to 1 ball radius past the initial cue ball location. We pause again to stabilize, then move upwards for clearance above any moving balls. We can see each of these states in the simplified video. The goal position of each state is used as an endpoint in interpolation. We set the number of keyframes and amount of time between each pair of endpoints. We determine the rigid transforms of the Q-tip for each endpoint with respect to the world frame, and interpolated between them using Drake's piecewise polynomial first-order hold and piecewise quaternion slurp. Trajectory generation provided us with a list of frames and timestamps for the end effector, so we translated this to joint space using inverse kinematics. Then the inverse dynamics controller commands the robot to run through the 5 states, and we visualize this in simulation.
In this example, the robot selects the red ball and the bottom right pocket since this combination has the highest allowed angular deviation, and it successfully sinks the ball following the trajectory. In 10 trials of spawning 5 balls in random locations, the robot was able to sink the ball every time. We made a number of simplifications in the implementation of our robot, such as only considering direct hits or keeping the robot stationary on the left side of the table. Next steps could include considering bouncing the cue ball or target ball off the walls of the table, improving the resolution of collision geometry, adding a perception system for multiple shots, and adding a mobile manipulator. Our current robot can accurately select and execute a single shot from a stationary position, but there are still many improvements to be made.